Welcome, everybody, and thank you very much for joining us for this video web seminar, Introduction to FaultManaged Power Systems, Revolutionizing Power Delivery for Structured Cabling. The seminar is being sponsored by Belden and by VoltServer. We thank them very much for their sponsorship, which makes this session possible. And we thank them for offering up the experts who are going to deliver today's information. Those experts are Stephen Eves, who is the founder and CEO of VoltServer, as well as Ron Tellis, who is Technology and Application Manager for LANs with Belden. If you looked closely enough when you registered for this event, you would see that Ron was actually labeled LAN Geek as a title for this session. And while that might not be his official title with Belden, I think you'll be sufficiently impressed with what Ron and what Stephen have to say today about FaultManaged Power. We are truly pleased and honored to have these pioneers in FaultManaged Power Systems delivering this information to you today. A couple of housekeeping things. Questions are welcome throughout the seminar. We're going to have a Q&A session to the extent that time allows. To wrap up, after the presentation is complete, we'll get into some Q&A with Stephen and with Ron. So please send your questions as you think of them, as they come up during the course of the presentation. Also, if you are a BICSI credential holder or an AVIXA credential holder, this seminar qualifies for continuing education credits from both of those organizations. I have detail about that credit and us delivering an attendance certificate to you. I'll get into that once the presentation is complete and before we get into the Q&A. For now, though, I thank you once again for joining us, and I'm pleased to turn it over to Ron from Belden, who's going to kick off the technical session today. So Ron, whenever you're ready.
Yep, thank you very much. So I'd just like to run through the agenda real quick. First, we're going to go through, what is Class 4 fault-managed power systems? They're very synonymous. We're also called digital electricity. So we'll get into all that. Different certifications for the cabling and systems have been developed for this new technology. And likewise, the codes and the standards have also been adapted to allow this. So at the end, we'll show some success stories that we've had with VoltServer on several different applications, and then lastly Q&A as Paul said. So why are we here? A while back, I ran into a hospitality integrator that was powering their pond system using something that I'd never seen before. And what I found was that it was a VoltServer digital electricity transmitter feeding a digital electricity receiver, and that was supplying power to the ONT that was supplying power to the access point. From that, I reached out to VoltServer and asked them, can you tell me more about this? And from that conversation, we found a lot of ways that we could help each other. Specifically from Belden, we designed and optimized some cables for their technology, several different gauge sizes, different ratings, different constructions, and then we worked with you all to get it certified. And we were actually the first to have a Class 4 certification on our cables. We've had success in several different venues, hospitality, within transportation, agriculture, and public venues, and the list can go on. And this is only the beginning. So first, what is Class 4? So there's several different definitions of the classes within the National Electric Code, and I copied the definitions here and give credit to the 2023 National Electric Code for these. We have 4 different classes. These are classes of power delivery that are not your typical mains type of or branch circuits. Class 1 is a little hard to explain. It's more closely related to our typical power that we have coming into our walls. So I don't want to focus there. What I want to focus on is the Class 2 and 3 and 4. And if you look at the definitions of Class 2, you may know Class 2 better as power over Ethernet. Not saying that all Class 2 is power over Ethernet, but power over Ethernet is a Class 2 system. And it describes the portion of the wiring system between the load side of a Class 2 power source and the connected equipment. Due to its power limitation, a Class 2 circuit considers safety from a fire initiation standpoint and provides acceptable protections from electric shock. Now, I underline that definition because I want to make a statement in regards to Class 4. Class 4 is a little different in the definition here is the portion of the wiring system between the load side of a Class 4 transmitter and a Class 4 receiver or Class 4 utilization equipment as appropriate due to the active monitoring and control of the voltage and current provided. A Class 4 circuit considers safety from a fire initiation standpoint and provides acceptable protections from electric shock. The reason I have those two phrases underlined and in bold is because you see they're both the same context. They're both as safe from fire initiation, and both are as safe from electric shock. And I think that as we go through a little more in depth, you'll see that one may argue that Class 4 is actually safer than Class 2. So what does this mean from a cable initiation standpoint, certification standpoint? So I have the different classes on the top. And as I said before, we have safety from fire initiation from Class 2, 3, and 4. But then if we also want to have protection from electric shock, that's only available in Class 2 and 4. So the listing for those cables are as shown. The CL2 is the general purpose, the R indicates riser, P plenum, and X is limited use. We have those same certifications except for limited use for Class 4. So these Class 4 circuits, which are really cables in our lingo, can be utilized in the same pathways and spaces as what Class 2 cables are. The important thing to remember, though, is that the cable rating on these cables are not listed or not written down on the cable, and that's done for a purpose. The reason that Class 2, 3, and 4 cables do not have the voltage rating on them is because we don't want somebody that doesn't understand that it's a Class 2 or 4 cable pick it up and see that we're 150 volt, 300 volt, 450 volt, and say, "Oh, I'm going to wire my lamp with that." That's not we don't want that to happen. So on purpose, within the NEC and UL, we do not add that to the cabling. But if you look on the technical data sheets for those cables, you will see what the voltage cable rating is, and you'll also here. Please note, a PoE cable, which is our category cable typically, has usually a 300 volt rating. Some might have less, but the Class 4 cable is a 450 volt rating. So it's really important to know that, because you can't just use category cablings for this powering in most cases. The other important thing I want to point out with the cabling is that the devices and the cabling must be marked as with the class listing. And I gave it an example of what that print string would look like on a Class 4 cable. And you can see here Belden Digital Electricity, and here's our part number. It's an 8-pair 16 gauge. It's been certified by UL as CL4. It can handle the jacketing temperature rating is 105 degrees Celsius. It's this particular one is sun resistant and wet location ability certified, and it's also dual listed to CL3. And then we have the footage at the end. So it's very important to note that the cable markings that are certifications that I have in the table above are also on your cable, and that's what I wanted to point out here. Steve?
Thanks, Ron. Hi, everybody. I'm going to talk a little bit about what a fault-managed power system is and why people would use it. All of this sort of originated from the expansion of digital infrastructure, digital convergence, as it's called sometimes. More and more buildings and factories are going out there and implementing IoT and digital devices that contain two things. That contain compute inside the device to process data. They need to get that data back to a central location, and the devices need power. And that's expanding exponentially in the world. But electricity hasn't migrated as quickly to the digital world. So fault managed power is a flexible, rapid installation process that combines data in the same channel or in the same cable. As Ron was talking about cable types, many of those cable types will also contain fiber, or they can contain communications copper in the same jacket. So this is all about combination of power and data in the same channels that installs very quickly, like class 2. So the main components are transmitters and receivers. So you have the main supply coming in from the left on this diagram, and you have a class 4 transmitter. So you're crossing classes there. As Ron pointed out, the mains power coming in could be classified as class 1, or sometimes we call that chapter 3 power. That's designated by that section of the National Electric Code. It comes into the transmitter, and at that point it's converted into a class 4 circuit. The output of that transmitter becomes a class 4 circuit space, and it remains as a class 4 circuit until it arrives at the receiver input. And when it leaves the receiver, it could be a whole new class again. As the diagram is pointing out, there's a class 1 output here shown on the upper right of the diagram, but it could very well be a class 2 circuit too, that the receiver could combine power conversion so that its output is again class 2, or it could be an inverter that turns it back into an AC output. So let's talk about the different types of faults in the system, starting with shock. FMP systems have to manage shock in multiple ways. So you could have a line-to-line fault, right? Or you could have a line-to-ground fault in different modes. It could be hand-to-foot, foot-to-foot. All those things have to be considered in the safety design of the system. And I should point out that conventional systems up to this point have not been able to detect line-to-line faults. Many of you might be familiar with ground fault interrupters, but remember that those are protecting from a fault from a line connection to earth. Like in the lower part of the drawing where the little person their feet is on a ground plane and their hand is on one of the line conductors. Currently, there's no known technology that can detect that kind of fault and respond to it in any way that provides the level of safety needed for certification. These systems, fault-managed power systems, actually detect the difference between a load device at the output of the receiver drawing a load and a person that might be touching the lines, and they'll interrupt power if that person touches the lines. All these things are critical to being able to install like a class 2 circuit as we know now. So those rapid installation techniques in a commercial environment that doesn't require conduit, just like a PoE cable or Ethernet cable. Here's another resistive or arc fault depiction. Now, arc faults we're familiar with, to those in the industry that have dealt with AC power. Arc faults we have arc fault detectors that are also often combined with ground fault or even circuit breaker capabilities. But what has not been detected before in conventional systems up to date is what's called a resistive fault. And many of you probably have, it's either through your personal experience or through somebody you know might have experienced a resistive fault. It occurs often when you might have an AC outlet in your home, and if the screw is not tightened down enough on the wire connecting to the AC outlet, you could develop what's called a glowing connection. It'll start to carbonize and change composition and eventually turn into a heater rather than a conductor. It'll go to a high resistance state or high enough that if you plug a toaster oven into that outlet, it will heat up enough to melt down the outlet devices. And it's a very common cause of fire, electrical fires. That particular fault, again, has not ever been detected by conventional technologies. It's very difficult to detect because it's not a touch fault or a ground fault. It doesn't arc at all. And to the circuit breaker, it's not actually drawing more power than the circuit is rated for. So that is why it's such a problematic fault and such a cause of problems in the field a very dangerous fault. So one class of fault managed power systems will detect resistive faults. They'll be currently in the standard, there'll be what's called Annex A and Annex B systems. And Annex B systems will have the ability to test this resistive fault and respond to it. Annex A systems will not have the detection, but they'll require special installation practices for that type of installation. Here's an overview of the faults that we're talking about and what has been done conventionally up to date with electrical distribution and what fault managed power does. So you could see in conventional, let's take an AC final distribution circuit, like a 110 volt circuit in your home. You can obtain line to earth, ground fault, or arc fault, right? Line to line is very problematic. Usually ground fault detectors are going from a line conductor to earth, and arc fault is also very difficult to detect line to line. It takes a long time to develop. By the time you're detecting arc fault in a line to line condition, it's already carbonized. Series arc is available with arc fault detection in parallel. And so, a series arc would be something where you actually disconnect the wire by a certain degree, and then it jumps through the ends of the wire to continue current to the load device. Same thing with parallel arc. If you were able to create enough of a conductor between the line conductors, it would arc off in parallel. All those things are detectable now, but as I mentioned, line to line resistive faults or series resistive faults have not been detected before in previous technologies. And of course, what we talked about in terms of a touch fault has not previously been determinable from existing technologies. All those things are now managed in a fault managed power system. You can look at the overall technology as taking something that's an inherently dangerous source, right? Today's technologies sort of create a source voltage and current that is distributed into the circuit, and then sort of external safety devices then manage that circuit so that it doesn't hurt somebody or cause a fault. In fault managed power systems, the source or the dangerous conditions are managed by technology, digital technology at the transmitter. So we'll talk a little bit about some of the success stories that we've had with fault managed power systems, and also noting that VoltServer was the originator of the technology class. But as you'll see in the future, there's multiple vendors starting to produce this equipment. And so as we move forward, there'll be multiple options to obtain fault managed power systems. Right now, it's sort of a single source situation with VoltServer, but that will change very quickly, particularly with the new UL standards and National Electric Code entries that are supporting the technology. Just so we open up the conversation a bit in comparison, what we have here is power over Ethernet installation, which many of you might be familiar with, and there's millions and millions of ports distributed in the world now. It's been a very successful technology, and I should point out that it's actually complements fault managed power. It's not a competitive technology. It ends up being an endpoint device where a fault managed power system will often power this entire PoE switch in a zone, and then the PoE switch will manage all the smaller loads. To date, fault managed power systems that VoltServer makes, it's expensive to produce a fault managed power system that's only delivering, say, 10 or 20 watts that with maybe a Wi-Fi access point might draw. So it actually makes more sense to deliver a lot of power with the FMP system to a PoE switch at maybe 1,000 watts, and then the PoE device then distributes it. And as many of you know, there's distance and power limitations with PoE. With the latest standard, with 802.3, We're currently at about 90 watts at the source, and as usual, the max distance is 330 feet or 100 meters. It's quite lossy at high power at long distances, and that's another reason why it complements fault managed power so well. By reducing the line lengths of the PoE nodes, you get higher efficiency and actually better data quality. So with the world transforming into thousands, well, I should say millions of IoT devices, but there might be hundreds or thousands of those devices in one building, it's getting very difficult to have long line lengths where you're drawing Ethernet cables all the way back to a closet in the base of the building. You get giant cable bundles, and it's quite lossy, as I mentioned, from a power standpoint. This will give you an overview of PoE versus fault-managed power system. The current standard is 802.3 BT on PoE. And the reason why there's not a standard listed for fault-managed power, there are safety standards that have been launched, and you'll see those below, UL 1400-1 and 2. But currently, the different manufacturers have not reached an interoperability standard. So there's no interoperability or IEEE standard that would designate that. For a little while, it's going to be a bit of Wild West as the new just like it was in Ethernet and other early technologies. It's currently a proprietary format, so you need a VoltServer transmitter to work with a VoltServer receiver, and we're not compatible with someone else's receiver. But that, like all these things, will eventually migrate to standardization. In terms of code, it's NFPA 70, the National Electric Code, and PoE is currently under Article 725. And so is actually, when I use the term digital electricity, current digital electricity installations are Article 725 installations. And as time goes on, more and more will migrate to the dedicated standard, dedicated article, I should say, which is Article 726 under the National Electric Code. That became adopted in the NEC in 2023. And as we'll talk about in a little while, it takes a little while for the states to adopt, municipalities to adopt NEC. So in terms of Article 726 qualification, as many of you know, something has to be listed to be installed in buildings in the United States and in Canada. And so that listing standard is currently being evolved. So the testing for these systems is going on now with more than one manufacturer. And we expect on the VoltServer side, somewhere around the first half of 2023, we'll obtain our certifications under the new standards, and then it can install under Article 726 in the municipalities that have adopted it. So in that meantime, we'll still be teetering back and forth between Article 725 and 726 installations. The wiring standards, you can see, are both under Article 722 in the National Electric Code, and the safety standards, as I talked about before, PoE and digital electricity current implementations are UL 62368-1 listed systems, and then fault-managed power will be under the new UL standards, which are UL 1400-1 for the equipment, and UL 1400-2 for cables. 90 watts, as we mentioned, on PoE. Fault-managed power systems, because of that thing that I mentioned, where the source of electricity is rendered to be safe at the source, at the transmitter, it doesn't really have any technical limit. It is limited in voltage, so the standard would go up. It supports up to 450 volts DC, the new 1400-1 standard. So anything that you could get under DC power at that voltage level is sort of game. I mean, the cables, the different manufacturers will be making different gauges to support those power levels. But right now, digital electricity is roughly 600 watts per pair at nominal distances. Our channels can go up to 1,000 watts per copper pair at shorter distances. And And then our maximum distance is 2 kilometers. That's not again, that's not a UL 1400-1 thing. That is an engineering constraint that we currently impose on ourselves to maintain reliable transmitter to receiver span. All these systems will be tested at their maximum distances and maximum power levels. So it could evolve to longer distances or higher power, and then we need to go back for certifications when we do that, like a lot of manufacturers do. And then max power at max distance, we're putting one sort of example for digital electricity, and at 2 kilometers on 4 pairs of 16 gauge, it's about 300 watts. So at those long distances, we have to derate, but sometimes it makes sense to get power out to a remote location that really needs it at those distances. One example, for example, is 5G small cells, when you're going at, transmitting across utility poles for long distances to set up a 5G node. So benefits of fault-managed power. As we talked about before, fault-managed power is a modernized form of electricity transmission made for digital transformation. So it installs with the same practices as Ethernet or PoE. It has lots and lots of more power, about 20 times the power and 20 times the distance as PoE. So in effect, it's not really a replacement for class 2. It's a replacement for conventional power distribution. So you can power things. You can power things like whole HVAC units or whole rooms of lighting, things like that, things that you would normally do with industrial level power. It runs thousands of feet on very skinny conductors and has system monitoring and control. So you're looking at a digital technology that actually embeds data within the FMP protocol. So when in the VoltServer implementation of FMP, we're sending pulses of power that also have data interleaved with that power. And that's sent as a discrete pulse that's from one place to another, and it's checked every time those little packets go out. So when we make those packets very, very small in energy content, and we're tracking every one, we can tell if that packet is going into a human body or a source of fire versus going to the right place, which is a remote load. You can run digital electricity extremely easy. If you have experiences of having traditional conduit-based power installed versus an IT installation, say of Ethernet or USB cable, that'll give you an idea of the difference in speed and ease in terms of deployment. And it uses a lot less materials in terms of ESG and sustainability benefits. Because, as we mentioned, you're distributing an inherently safe form of electricity. You don't need all those things after the power source to protect people and buildings from it. So at the very easiest way to look at it is just by eliminating hard conduit runs. In a typical building, you're removing thousands of pounds of intensive carbon-intensive steel or aluminum. So that's one of the other benefits of fault-managed power. This slide talks a little about adoption. This just comes back to keep everybody sort of calibrated on what's going on, right? There was a National Electric Code article that was released in 2023 that goes hand in hand with UL standards that allow systems to be listed and installed in buildings. And then the other thing that has to happen is there needs to be a bunch of training and adoption so that folks in the field know how to install it. And so different states have different rates of adoption. And this graph here just kind of talks about where different states are. You can see that the green is some of the older code states that they take a long time to adopt code. And then the purple is more rapid adoption. Ron?
Thanks, Steve. Very, very good summary. And I really do appreciate all the safety aspects that you brought out. That is not quite evident when you just read a table. I mean, it's very encouraging to see that this technology is really safe and deployable and makes it easy to put things where they're needed. And I think we'll see that as we further go into this. One of the things that does come up often, we just looked at the adoption, and the question is, what if I don't follow the NEC? What if I'm outside of North America or Canada, or if I'm using an earlier version of the NEC? Can I still call this a class 4? The answer is no. But you can deploy digital electricity, and digital electricity is listed as under IEC 62368-1 as a limited power supply, and it also follows those wiring the wiring practices of 725. This has been certified by a NERDL. It's a nationally recognized test laboratory, and those are qualified by OSHA. So that's how we know that this is safe, and that's how we're able to have the success that we've had in deploying these systems prior to the adoption of this new class 4. The last question that's up there is, can I use any FMPS? And the answer is, I don't know. I don't know what the other people are doing. I don't even know who the other people are. I know a few. But I do know that VoltServer is the only one that has taken the extra effort to pioneer the waters into how to deploy this technology given the parameters that are available, and then also change those parameters so that they can open it up to other sources as well. Installation considerations are tantamount to adoption of this technology. And I just like to get into the installation part of it here within the NEC. And within the NEC in Article 726, there is the Article 139, which describes the separations. And it has here that Class 4 circuits are allowed to be in the same raceway and pathways as jacketed cables of our other what we call limited energy cables. So everything that we've done before with power limited fire alarm, optical fiber cable, category cabling, or CATV or low power broadband, all those cables have been treated the same in the National Electrical Code in the past, and they still will in the future. And Class 4 falls into that same category. Now, it does take a bit of knowledge to do this. Not anybody can just grab a hold of a cable and get a transmitter receiver and say, I'm going to go do it. You need to be trained properly, and we are working with some of the contractor organizations, NSCA, CEDIA, and BICSI to be specific. They're very much in tune with making sure the contractors know what's on the horizon, and also how to take advantage of this new technology and deploy it in their world so that they can pivot a profit. Exactly is what they're doing. One of the big things that this organization, these organizations have gotten together and making sure that all the legislation is in place, and also the training is in place with NESCALA, and creating what's called a labor classification. Now, if you went and looked at what we call the low voltage installer labor classification today, if you could find it, it's probably last time it was updated was 1984 or something like that. And it says that a low voltage installer has the talent of being able to fix video recorders. Let that sink in for a minute. Our installers are doing way more than video recorders. In fact, I don't even think we use video recorders anymore, except in special occasions or trying to bring out some old movies. Our installers are putting together complex systems. They're working not only in copper, but they're also working in fiber. and they deserve to be called integrators. And that's what CEDIA and NSCA are working with, along with Dixie, are working to create that classification in the OSHA labor classification as a integrator. And probably as that evolves and takes root, we're going to see other definitions of all these different categories or types of cables that these integrators can work with. Those different circuits will be called limited energy. In all, and that's my estimation. That's where everything's going. So we're going to see our terms for low voltage installer change to something like a limited energy integrator. So please be prepared for that, and do everything you can to help our installers to fall under that classification, so we have a bigger voice in the labor pool. So I know we already went through from the Mr. Digital Electricity himself. Sorry, Steve. Hopefully you're okay with that. But I was asked, what is digital electricity, by one of his employees, and the elevator speech he gave me was, it's the 5 S's. So if anybody asks you, what is fault managed power? What's digital electricity? What's class 4? Your answer is the 5 S's. It's the safe delivery, significant power over significant distance using smaller conductors, providing speedy deployment. Okay. And we've already said with the digital electricity, it's a series of pulses that are monitored, and if anything goes wrong in between the transmitter and receiver, it instantly turns off and prevents anything bad from happening from some type of fault. In relation to the significant conductors and power argument, I have here on the bottom a graphic indicating the calculations that I made to demonstrate how it's significantly less conductors to utilize this technology. Each one of the circles is a 4 conductor 18 gauge cable. With that 4 conductor 18 gauge cable, a single one using digital electricity, I can deliver 100 watts to 2 kilometers. Likewise, with that same cable, I could also deliver 2 kilowatts, but a much shorter distance at 100 meters. So keep that ratio in mind. Now, if I go back to the argument of class 2, I can still do these same things with class 2 cabling. And I'm talking here a DC line voltage type of class 2 power supply, not PoE. It wouldn't make sense there. But if you look at a typical class 2 using a DC power supply, with that same 4 conductor cable, I would need 18 of them to do 100 watts at 2 kilometers. Or I would need 18 of them to do 2 kilowatts at 100 meters. Now, mind you, it'd be a lot of soldering that would have to take place in order for that to happen, but you get the idea. That is where the 20 times rule comes into play. It's right there in the proof of the calculations that now, if I wanted to deploy a very large power, I can significantly reduce the number of conductors. That means less cables. You know, I'm a cable guy telling you you don't need as many cables. That's how significant this technology is. It allows you to do more things. It allows you to put components where they are needed, and that's why the success in distributed antenna systems has been taken off so well, because when you do an RF study to find out where is my wireless strengths and where are my weaknesses, and then you want to put an antenna where that weakness is, sometimes you would put a radio unit in that place or somewhere near, you don't have power. But with fault managed power, that requirement goes away, because now you can deliver that power and the data almost virtually anywhere. And just to make the point of how it's treated the same as how these cables are treated the same as PoE cables or category cables, I have here an ICT integrator installing a fault managed power cable in the same cable tray as fiber optic cabling. That's what the difference between the colors of black and green are in that tray. As I mentioned before, we work closely with VoltServer to develop the digital electricity cable. We tried to get every variant that they needed to handle virtually all of their applications. So we had all the cables had different shielding. It could be shielded, it could be not shielded, it could be copper only, or it could be a hybrid cable. A hybrid cable is one that has the copper conductors and the fibers. So now we can do power and data with one cable pull. The different gauge sizes are needed for the different power requirements. And then we have the ability to put multiple pairs in these cables to also be able to spread out that, use multiple power supply slots they have in the transmitters to deliver to the receiver. And then lastly, I just wanted to make a note, as I already said, that we worked with UL to develop the Class 4 certification UL 1400-2, and we were the first to obtain that certification, not only for copper, but also for our hybrid copper Class 4 cable. So, Steve, I'd like for you to describe some of the success stories, if you don't mind.
Yeah, thanks, Ron. This is a really fun installation. The case study. This is the Circa Resort and Casino. This is on Fremont Street in Las Vegas, old Las Vegas. It's a premier resort. We went there and visited. We did our sales meeting here. You could see it's got multiple pools down on the bottom floor and a giant screen where they do events on that screen, and then betting. So you're sitting in the pool and drinking and betting. Premier Las Vegas type venue. It's got 777 rooms. This was a unique installation in our sort of evolution at VoltServer because it was way beyond powering communication systems. Although it had DAS and Wi-Fi, it also powered, well, almost everything in the rooms, in those 777 rooms. There's still a few AC outlets in there. At that time, we hadn't evolved our inverter technology. In the future, we'll actually cover AC outlets as well as everything else. But the customer was very unique, and they were looking for something that was very monitorable and controllable for their infrastructure, so that they can monitor and see, hey, is there light out in a room, or is there a problem with the electrical system? But also, by having a fault managed power system, you are able to centralize energy sources. So what I mean by that is, if there's an outage in this building, the transmitter units are down at the bottom floors of the building. It's actually only one room in one floor, but it has a generator feed. And so if power goes out, the generator kicks on, and all the critical systems like building management, basic lighting, and controls in the rooms are all on that generator feed. And the as the owner says, the guests barely even noticed something happened at the entire building level. So this was a lot of fun. It was a big installation reflective of what we call our intelligent building installations. I always like to call out Sinclair Hotel in Fort Worth as the first sort of implementation of intelligent buildings. Sinclair adopted digital electricity very, very early on. And that's another great result, great resort called the Sinclair Marriott in Fort Worth. And there's a couple other great implementations like this. Here's another implementation. This is a very sort of typical, I'll call it communications application with VoltServer. So this is the Hard Rock Stadium, and you could see why Ron is with us right now. It was like a 700,000 linear feet of cable. And what I remember about some of these installations is that what I saw was that there was more fault managed power installed in these installations than regular electricity. When you look up into the ceiling, all you saw is green cable, just huge amount of, and that is just an indication of digital convergence, how these stadiums in a way are becoming a big computer, right? There's tons of data moving through these stadiums. There's monitoring devices, there's displays, all moving power and data in the network. Just again, digital convergence is driving these applications. It's using the full capability on run lengths. You could see from 500 to 2,500 feet. And as Ron pointed out, it's critical to these customers to get in and get out fast and get the job done once. And so the customers, which might, in these applications, the customer might be a Verizon or a T-Mobile or an AT&T, and they're able to use the existing cable trays that are in these buildings and drop in fault managed power without doing hard conduit runs. So it's as much about cost as it is about speed. Getting in and out of these facilities and getting them running is hard money too. It's not as well characterized sometimes as just the cost or the price of the installation, but it's just as important to these customers. This is an indoor farm. This is Hardy Fresh in Florida. This is a very large sort of, another sort of reflection of the evolution of times here, that with climate change, it's getting more and more difficult to grow premium products outdoors. So these facilities, these what's called a vertical farm, is all the growing is done inside without sun. So it's LED lighting. It's about 1.1 megawatts of installed power, powering like thousands and thousands of these lights. And you can imagine how complicated power distribution is with traditional power at these power levels. Digital electricity makes this all a sort of network. So not only does it provide power, but as we've talked about in this presentation many times, it's also a channel for data. So these are highly controlled environments that contain thousands of sensors and controllers and valves and what's called a programmable logic controller, which is an industrial computer. There's hundreds of those in these facilities. All of them are moving power and data. So coming back to the same thing, digital convergence is about getting data and power to these compute devices that are everywhere now. So we're powering controls and lighting in this application, and it's also a full software suite that allows the customer to manage the facility. Ron?
Yeah, it just would be remiss if we didn't show that when it comes to delivering data with fault managed power, with these long distances, the obvious choice is fiber, and that's why we've gone down the path of creating a digital electricity hybrid cable, so that we can deliver power and data to these devices wherever they're needed. So just to make a point that what we do as a manufacturer, we connect networks, we connect systems, and we can do it with copper, with fiber, with coax, with whatever. So I just wanted to show an example of how we work together with not only VoltServer but other partners when it comes to the systems like the distributed antenna systems or the passive optical LAN systems that usually requires the suite of Fiber Express components to go along with those.
Okay, so to get close to a summary here. So right now, as we mentioned, fault managed power is a technology class now. It was originated by VoltServer, but you'll see other manufacturers coming online now. For now, we're the only folks with stuff in the field. And, you know, it's a single source right now. I agree. But the delivery of value that comes out of these systems is very high. And that's why we have business, because the difference between conventional power installations and a digital electricity installation is very high and outweighs you know, the thought of a new technology, the risk of adopting a new technology and using proprietary equipment. We actually welcome the new manufacturers coming online. It's a big pie. We're talking about converging the whole worlds of electricity and data into one converged space. As Ron called, when we're talking about word use like integrators, we're talking about not only the equipment, but the convergence of skills and labor classes to bring the efficiency of installing buildings and installing factories to a higher level to keep up with everything. Everybody knows that it's tough out there right now from a cost standpoint and from a labor standpoint. Whether you're an electrical contractor or a manufacturer, the problem is still there. People need to build more things more efficiently. It's a big pie, and I think we can all participate in it. So from the VoltServer side, we've sort of seeded the ground with thousands of installation points and about 50 megawatts of installed power now. Each one of those facilities now, when you see a farm or a stadium, is often hundreds of kilowatts and sometimes megawatts of installed power. So we currently focus on big stadium installations, airports, offices, hotels, and as I mentioned, new areas like EV charging and indoor farming. Really, the world's the oyster on this stuff to everybody, not just VoltServer. It's an improved way to install power.
Just to follow up on that, Steve, with your all the different facilities that you've powered, I think we've done something close to over 4 million feet of linear feet of cabling. That's many different conductors in those cables as well to help supply that. So the key takeaways that I'd like for everyone to take away from this is that it's class 4 fault managed power is just as safe, if not safer, as Steve's get demonstrated than class 2. It's installed the same as class 2 and class 3 cabling. Class 4 cabling is not the same as class 2 cabling. It has a 450 volt rating. And it's important to note that the transmitter receiver, which is your equipment, and the cabling must be listed to UL 1400-1 for the system and -2 for the cabling. Remember the 5 S's if anybody asks, what is digital electricity, what is fault managed power, what is class 4? They're all the same in the context here. The 5 S's help there. And if you have any questions, you can go to the VoltServer website. There's plenty of great use cases there and videos. That's how I first learned about it. I've since then brought together many different blogs and white papers and other webinars and use cases as well. And we have a whole landing page on Belden.com, which the URL is giving at the bottom. So with that, Patrick, I turn it over to you.
Thank you. Thanks very much to Stephen and Ron for the information provided. We'll get into Q&A soon. We've got a few minutes before we get to the top of the hour, so I'll quickly go through housekeeping. To those of you who have credentials from BIXI or from AVIXA, this session qualifies for continuing education for those credentials. The way that it works is, thanks for joining us live. We're live here today, August 24th. When we wrap up, we will send an email to you, to the address that you provided to us when you're registered. That email is going to have a link that brings you to your attendance certificate. That attendance certificate is going to have the title of today's session. It's going to have your name on it. It's going to have today's date. And it's going to have a code that BIXI in particular recognizes as this course for a continuing education credit. Also, the seminar is going to be available for on-demand viewing for a number of months. So if you liked what you saw today, I know it's going to be worth another watch and listen. So know that you can come back and watch it over the next several months to refresh. If you're watching it for the first time on demand after the 24th of August, your certificate will be available to you and will be emailed to you after you complete a knowledge check. We're just going to ask a couple of questions about some of what was delivered here today. Once that knowledge check is completed, the email will be on its way to you with your attendance certificate. So thanks very much for bearing with me through that. I know we've got a few minutes for Q&A, and I'm going to be looking in a couple of different directions here. We have a number of questions. I thank you for those. Here are the few that we're going to get to. If I could start with you, Ron, a question about cable construction. Does the fault managed power system require a separate conductor cable? Can copper conductors in a sort of fiber optic composite cable be used? Talking about, for example, powering a remote switch that that's fiber fed. And Ron, if it's appropriate, I can pull up a slide that you delivered. If this one is worth a visual for the audience as this question comes up. So what's the construction of the cable that can be used?
Yeah, so the construction that you just described is what's called a hybrid cable, and that's the second one from the left. It shows that there's copper conductors for the fault managed power, the digital electricity power circuit, and then the yellow is the fiber, and that's what's delivering the data to the end device. So you'd have to strip back the cable, expose those, splice on connectors, and then have the copper conductors go into the screw terminals typically, and that's how it would be used. So yes, you can have both under one cable sheet.
Thank you. And a number of questions came in about cable construction. Some of them came in before you presented this slide. I think that may have answered some of them, but there were questions about, does the cable need to be wrapped in foil? It looks like some are and some are not. It sounds like there are a number of options in terms of cable construction for users.
Yeah, if it is totally used outdoors, I think that you have to follow a different code, and that's the National Electric Safety Code. And within that code, it does require that all cables have a foil. When you come indoors, that's when you follow the National Electric Code, and that's and that is more about the safety or composition of the jacketing, and that's why we have the riser and plenum ratings. And foil is not required in that sense.
Thank you. Thanks very much. Going to get through as many questions as we can. Stephen, if I could ask you a question or two from attendees. One asks, is there any feedback to the transmitter from the receiver?
Yeah, there is feedback from the transmitter that it's actually bidirectional communication between the transmitter and receiver that is not critical to meet safety requirements. So it's part of our design practices to make sure that everything can be determined on the transmitter side if there's any safety-related event. But it is important to transmit data. There's a lot of sort of control functions that folks might want to know, like what is the temperature of a device at the other end of the circuit. Our channels, our data channels are low bandwidth channels that are highly resilient channels that are good for control. And high bandwidth stuff like video would then go on the fiber that runs along with the cable.
Thank you. Thanks very much. Another question from an attendee asks if there are any international standards that are in the works, for example, something from IEC or maybe some type of European version of the UL 1412 that was brought up during this conversation. Anything in the works internationally?
Yeah, that's actually easy. So, digital electricity systems are currently installed internationally. So, as many folks know, IEC 62368-1 is an international standard. In the US, the current systems are approved under a section of that called LPS, or Limited Power System categories. And that's what lets us install under Article 725 currently, which will migrate to 726. But internationally, we just qualify as, many folks might know as an ELV, extra low voltage source. because we qualify. 62368 is perfectly compatible with digital electricity, and the systems are qualified under that standard.
Thank you, Stephen. Thanks very much. A final question for either or both of you, if you care to one or the other cares to answer it in the minute or two that we have left. The difference between FMPS, fault managed power systems, and digital electricity. Stephen, I know a couple of the slides, that you brought up mentioned, that there are differences. Digital electricity, I won't try to answer the question, but I understand there are differences. And for some members of the audience, it would be worthwhile to reiterate those, if you don't mind.
Yeah, so you can look at digital electricity as a type of fault managed power system. And I'll be careful to give respect to the standardization process and everything else. To avoid confusion, we're calling ourselves a type of fault managed power system. FMP is a generic term for these types of systems that meet the safety category. It's essentially a class 2 like safety category. And so other manufacturers will come out and they might brand their version of FMP a different trade name, like our trade name is digital electricity. They'll all be FMP systems, and what the industry will work towards is interoperability next, where we can work together like Power One receiver from another manufacturer with our transmitter, vice versa.
Thank you. Thanks very much. I really appreciate it. I know we've gone past an hour, and many of our attendees have just 1 hour to devote to these sessions. I know that we have many questions that came in we were not able to address here today. To those of you who submitted questions, I offer my sincere thanks for your attendance, for your interest, and for the questions that you submitted. I'm not going to make promises for anybody on our panel or any organization, but I will tell you that questions that you submitted have been retained. It is possible that at some point in the future, you may receive an offline correspondence related to a question that you submitted. So we will be signing off in a moment, but I don't want those of you in the audience who submitted questions to think that this is necessarily the end of the dialogue. It's possible that you may be hearing something in the way of follow-up to a question that you submitted here today. Again, sincerely appreciate your interest. I know there was a great deal of it. I can see a list of questions that came in. They're all very worthy and very pointed about the technology and its capabilities. So I thank Belden and VoltServer, as well as Stephen and Ron for this presentation. Thanks to every member of our audience who joined us. We hope that you'll come back for another seminar with us sometime. Please keep VoltServer and Belden in mind as well. A lot of great information coming from those organizations. And we hope that we see you all again sometime soon. Thanks, everybody, for your participation today. We sincerely appreciate it. Thank you.
Thank you, Patrick.